Today we're going to be talking about using the derivative, so our first and second derivative, to sketch a graph of our original function. So, okay, notice what we're given here. Hopefully it's not too hard for you to see, but we're given the derivative. So we need to find the local extrema, increasing, decreasing, and concavity, and then eventually graph this. Well, we figure out our increasing and decreasing by setting our derivative equal to 0. At the same time, I'm going to do a little bit of algebra for us and factor out. So we have x equals 0 and 3 for our critical points. So I put 0 and 3, and then plugging in a negative 1. This 8x squared is always going to be positive, so really I just have to look at the sign of this x minus 3. So I have a negative. When I plug in 1, I also get a negative. When I plug in 3, we get a positive. So we are decreasing from negative infinity to 0 and from 0 to 3. Now notice how I broke that up. I broke that up because 0, technically we're neither decreasing nor increasing. And we're increasing from 3 to infinity. Okay, where our local extrema are. Our local extrema happen 0. There's no local extrema because our derivative doesn't change signs, but since we change from negative to positive, we have a minimum at x equals 3. Now we need to find concavity, so find your second derivative, which is the derivative of the derivative. Hopefully you know that by now. If you don't know that by now, I have failed you as your calculus teacher. I set that second derivative equal to 0 and factor out. So our critical points for our second derivative are 0 and 2. Again, I was a bad calculus teacher on this first one. I should have told us that we're looking at the first derivative. Here we're looking at the sign of the second derivative. So we have a 0, we have a 2, so if I plug in negative 1, I have a negative times a negative, so that's a positive. Say I plug in 1, I have a positive, negative, so that's negative. Plug in 3, positive, positive. So we are concave up on the interval from negative infinity to 0, and from 2 to infinity, and we are concave down at, on an interval. Remember, concavity is an interval from 0 to 2. Okay, now we need to take all of this into mind and sketch our graph. Make sure you label your axes so you know what we're looking at. Okay, we have no starting y value, but I know that I'm decreasing and concave up. So I'm decreasing concave up from negative infinity to 0. So pick a point that's a little bit lower. I'm decreasing, but I'm able to hold water. So decreasing, concave up. Or my slopes are getting bigger. Okay, now I start increasing from 0 . So I start I'm still decreasing, but I change concavity from 0 to 2. So I'm still decreasing, but my concavity changes to concave down. And I'm going to try and make this as smooth as possible. Concave down. It's all concave down. And then at 2, we change back to concave up. I have a minimum at 3. I'm still decreasing all the way to 3. So here my concavity changes, but I start being able to hold water. And then from 3 on, I'm increasing, but I'm concave up. So increasing, concave up. Okay, our next example has to do with using the graph of our derivative, and this is really important, the graph of the derivative, to figure out increasing, I apologize, excuse me, decreasing, and our coordinates of local extreme values. So we are increasing. So let's start writing this right now. F of x is increasing when f prime of x is greater than 0. So that's my justification. So now we need to see, when is this graph greater than 0? And I'm doing a really bad job highlighting this. Greater than 0, what is that? From -3, I can't do interval notation. What is my problem? For numbers less than -3, so from -infinity to -3, and whenever from 0 to 4. So whenever f prime of x is positive, so the actual graph is above 0. So from 0 to 4. Okay. Now we need to do decreasing. Decreasing. So we are decreasing when our derivative is less than 0. Okay. So where is this actual derivative less than 0, meaning negative? We are decreasing from -3 to 0 and from 4 to infinity. Now local extreme values. Remember, we have a max. A max happens when f prime of x changes from positive to negative. So where does this actual graph change from positive to negative? That happens at -3 and at 4. We have a min when f prime of x changes from negative to positive. So when I change from negative to positive, that's at x equals 0. Okay, our last example has to do with a chart. So deciphering from the chart the absolute extrema and where they occur, points of inflection, and our graph. Okay, so a max. A max is going to happen when your first derivative changes signs from positive to negative. So do I ever change from positive to negative? I'm looking at this sign of my first derivative. Even here, positive to negative, I have none. Okay, a min. When our derivative changes from negative to positive. I change from negative to positive at x equals 1. Anywhere else? Nowhere else. My first derivative doesn't change signs. Point of inflection happens when your second derivative changes signs. So it looks like it changes signs at 2. So our point of inflection happens at 2. Now, my best advice is, first of all, we label our axes. And then, since I give us some actual function values, write down this actual column. Put those actual values on your graph. Okay, 0, 3, 0, 3, 1, 0, 2 and 0.5, 3 and 2, and then 4 and 4. Now you have these values. Now look here to see what's happening to your derivatives. Okay, so I'm decreasing concave up from 0 to 1. So I'm decreasing, but I'm concave up. Now I'm increasing concave up. Increasing concave up. Still increasing, but concave down. So that's a point of inflection. And then increasing, but concave down again, but my derivative doesn't exist. So kind of something funky happens there. And then I kind of have it look like another little blip in my notes. So that technically our derivative doesn't exist there. The slopes of the tangent lines from here, from the left side and the right side, are not the same. Okay, that's kind of an overview. You're going to experience a lot of different types of problems in your homework, and we'll talk about those in class. Please, for me, make sure your lesson summary is submitted on time.